Yesterday we ended on talking about increasing and decreasing, and it may have confused you a little bit. So we're going to continue today, and we're going to look at increasing, decreasing intervals, first derivative tests, and we're honestly going to look at more than just this. Okay, so we ended on something like this yesterday, but we didn't call it the first derivative test. This is the first derivative test. If the first derivative of f is less than 0, then f is decreasing. So think about that. When it's less than 0, it's negative. So if the first derivative is negative, then our graph of f is decreasing. If f prime of x is greater than 0, then f is increasing. Well, think about that when it's positive. If the first derivative is positive, then our graph of f is increasing. We also have something called concavity, and I'll explain what that is in just a second. But concavity comes from the second derivative. All right, and I have two different things right here. If f is concave up, then the second derivative of f is positive, or you can think of it this way. If it's concave up when the second derivative is greater than 0. If f is concave down, then the second derivative is negative, or you can think of it as less than 0. Well, what do we mean by concave up and concave down? Okay, let's take this graph right here. And this was something hard for me when I first took calculus to understand. Well, obviously I can tell this is increasing right here on f, and this is decreasing. So the first derivative here is going to be positive, the first derivative here is going to be negative. But what about concave up and concave down? So I got concave down here and concave up here. So what makes it concave down and what makes it concave up? Well, concave down does not mean it's decreasing. Concave down means it's cupped. Like, think of your hand like cupped up. Cupped down. So if you think about this part of your graph is cupped down. And concave up, the graph is cupped up. So think about it, this part of the graph is cupped up. So when we talk about concave up, the second derivative is going to be positive, and here, concave down, the second derivative is going to be negative. Now, we have some other things that apply here. Say the second derivative test. Now, if f prime of c equals 0, and f double prime of c is greater than 0, then x equals c is a local min. You can think of it also as a relative min. Okay? So, we know it's an extreme value when it equals 0, but when this is greater than 0, we have a relative min. Now, here when the first derivative equals 0, but the second derivative is less than 0, it's negative. Okay, so therefore it's concave down. Then we have a local or relative max. And then we also have something called a point of inflection. I've got it written here, but I also have it written here. Point of inflection is a point where the second derivative equals 0 and the concavity changes. That means the second derivative changes from negative to positive or positive to negative at that point. If it goes positive to positive or negative to negative, then this is not an inflection point. It could the second derivative could equal 0, but it didn't change concavity. So much like f prime of x equals 0 suggests there is a max or min, but you have to check to see that the derivative changes signs at that point. Same idea here, just because f double prime equals 0 does not mean an inflection point. You have to see if it changes signs at that point as well. All right, so let's look at some examples, and make sure you have some paper. This can take some paper for this. Now, we want to find extreme values, where we're increasing, where we're decreasing, where it's concave up, where it's concave down, and also the point of inflection. So first off, let's talk about extreme values. Okay, extreme values. Extreme values are when the first derivative, so let's find the first derivative, are equal to 0. All right. And here, when I go to solve this, I'm just saving myself some room. You can go solve it. You end up with x squared equals 4, but don't forget when you take the square root, it's going to be x equals plus or minus 2. These are critical points. Okay, this is where our max and min could be. Does it have to be? No. Now we can test for max or min. So we're going to find the second derivative. The second derivative of this is going to be 6x. All right, so what we're going to do is we're going to find f double prime of 2 and f double prime of negative 2 and find these values. All right, f double prime of 2 is 12 and f double prime at negative 2 is negative 12. Well, let's look. This is greater than 0. This is less than 0. So what does this tell me about this? It means I have, okay, remember when it's greater than, when the second derivative is positive, I have a min. So I have a min at x equals 2, and I have a max at x equals negative 2. Now, if they ask why, here's your verification. Right here and right here. All right, because the first derivative equals 0, but then when we plug it in by the second derivative test, when it's the second derivative is positive, it's a min. When the second derivative is negative, it's a max. And let me tell you, it's hard for me to remember this. Okay? Now, intervals of increasing and decreasing. Well, here we can create a sign line, but sign lines, just remember later on, you'll hear me talk about this a lot as we get closer to the AP exam. They're not work. They do not grade this for work. Okay, increasing and decreasing are when the first derivative, when it's positive, it's increasing. When it's negative, it's decreasing. All right, so let's think about this for a second. Okay, think of something on the left side, say negative 3. So f prime of negative 3. Okay, if I were to plug this in, okay, 6 times negative 3 is less than 0. All right, so therefore it's negative. All right, f prime of 0, that's something in between. If I plug in 0, I get 0. All right, if you want to plug in something else, you are welcome to. And you know what? I just plugged this into the wrong thing. I plugged this into the second derivative. I'm supposed to plug it into the first derivative. This is the first derivative. So if I plug in negative 3 squared is 9. 9 times 3 is 27. 27 minus 12. I don't need to know the value. I know it's greater than 0, so it's positive. Now let's plug in 0. 0, that makes 0 minus 12, which is negative 12. So this is less than 0. So this is negative. And then plug in something on that side. We'll just say f prime of 3. Okay, 3 squared is 9 times 3 is 27 minus 12. And that's going to be positive. So I'm increasing. And guys, this right here is kind of part of your justification. Not only the sign line, but this. They can grade that. All right, it's increasing from negative infinity to negative 2, and don't use brackets, just use parentheses, and then from 2 to infinity. Now, where is it decreasing? It's decreasing right here in between negative 2 and 2. Now let's talk about concavity. Where is it concave up and concave down? All right, well, one of the things is you need to find where f double prime of x equals 0. Well, we already found the second derivative. It's 6x. All right, that's at x equals 0. So if it's going to change concavity, it's going to change here. So let's do the same thing that we did here. If I plug this into the second derivative, all right, on the left, say negative 1. All right, the second derivative is 6x. So negative 1, it's negative. Okay, here if I plug in positive 1, it's positive. So it's concave And the reason is, and still put some justification, say f double prime of negative 1 is less than 0, and f double prime of 1 is greater than 0. All right, so it's concave up from 0 to infinity, and it's concave down from negative infinity to 0. Now something else happens here. Didn't we set the second derivative equal to 0? All right, and we did. Remember what could happen. When it's set equal to 0, we could have an inflection point, but there was one other thing that had to happen. It changes concavity. Does this change concavity? Negative to positive, positive to negative, either or? And it does. So I have an inflection point, or a point of inflection at x equals 0. All right, so that's a lot. We talked about extreme values. All right, that's our local max and min, or relative max and min. All right, we talked about increasing and decreasing. And really, we can get our max and min, relative max and mins from this as well. If you think this is positive and this is negative, then it goes to positive. This is going to be a max, and this is going to be a min, instead of doing the second derivative test down here, if that's a little easier. All right, same thing. New function, the same thing. We're going to find our extreme values. Okay, that's f prime of x. Okay, that's 4x cubed minus 4x, or 12x squared. Okay, when is this equal to 0? Well, here, if I factor out a 4x squared, I'm left with x minus 3. Well, it's set equal to 0 when x equals 0 and x equals 3. All right, so these are going to be our critical points. Okay, where relative max and mins can occur. Well, we need to look at the second derivative. So let's go find the second derivative. 12x squared minus 24x. Okay, at the second derivative at 0 is 0. Okay, and what this means is it's not a min or max. So here, because this equals 0, on the second derivative, it's not a min or max. So the only min or max could be here at 3. So let's look at f double prime of 3. All right, if I plug 3 in to here, let's see, I end up with 36, which is greater than 0. Now think about it. When the second derivative is positive, okay, then I have a relative min at x equals 3. Okay, now let's talk about increasing and decreasing. Okay, increasing and decreasing comes from the first derivative. All right, but I put my critical points, even 0, on there. Okay, on the left side of 0, let's say negative 1. Okay, if I plug negative 1 into here, let's see, that's positive right there, and that's negative. So positive times a negative is a negative. Now let's plug positive 1 in. Okay, same thing. This is going to be positive, and that's going to be negative. Okay, now after, let's say 4. Okay, this part's going to be positive, and then that's always positive, so this is positive. All right, and here what I want to do is I want to say less than 0. Here I plugged in, say, 1, it was less than 0. And here I plugged in, say, 4, and it was greater than 0. I can't just have the sign line as my part of my work. It's got to be more than that. Okay, so therefore, I know that we're increasing on the interval from 3 to infinity, and I know we're decreasing. Now, it kind of stops here at 0. So what I'm going to have to do is I'm going to have to say negative infinity to 0 and then 0 to infinity. I mean, not infinity, 0 to 3. Okay, so just remember that right there. All right, and again, I don't use brackets. Okay, let's talk about concavity, up and down. Okay, this comes from the second derivative. And when it's when the second derivative is set equal to 0. All right, we've got to find the critical points of that. Think of it that way. 12x and then x minus 2. Where does that happen? X equals 0 and x equals 2. All right, so I can create a sine line with this. And again, I'm looking at the second derivative this time. I'm going to put 0 here and I'm going to put 2 here. All right, so f of double prime of negative 1. Let's look at that. Well, this makes negative and that makes negative for a positive, so it's greater than 0. All right, let's try it at 1. Okay, 1, that's going to be positive, that's going to be negative, so it's going to be less than 0. And then f double prime, let's say at 3. Okay, that's positive, so it's greater than 0. Okay, so what we can say is concave up on the interval from negative infinity to 0 and then 2 to infinity. And then concave down from 0 to 2. Now, let's talk about inflection points. Inflection points are when it's set equal to 0. Okay, we got 0 and 2. And when it changes concavity. Does it change concavity at both of these? And yes, it does. It goes positive to negative and negative to positive. So, points of inflection are x equals 0 and x equals 2. Now, let's look at a graph of this right quick. So I'm going to plug in x to the 4th minus 4x cubed. Okay, so I'm going to plug that in. Okay, zoom 6. And you can always check this. Now, if this was on a non-calculator part, which would be really what happens, then you would want to see it. Or you couldn't see it on a calculator, so you couldn't verify. Okay, if you notice, okay, this is decreasing all the way, okay, and we said something about decreasing from negative infinity to 0, and we can tell at 0 it kind of stops, and then it decreases some more. And then, I assume down here is where it's at 3, okay, and we said, look, relative min at x equals 3, so down here at x equals 3 is going to be a min, all right, and then it went back up, it's increasing from 3 to infinity. All right, so we're good on that. All right, so let's look at the concavity. So think about this as being cupped up right here. All right, and we said concave up from negative infinity to 0. And then it's concave down because it's cupped, think of this as cupped down from 0 to 3. And then it's going to be cupped up, all right, from 2 to infinity. And it changes. And then point of inflection, x equals 0. We kind of see how it turns. It changes concavity there. Okay, it didn't change increasing or decreasing, but it did change on concavity. And let's see if we can find the value. Let's see at 2. All right, it's negative 16. So if I change my window down to say negative 20, let's look at this point at x equals 2. And then I'm going to give you one to try on your own. I want you to pause the video and I want you to try it on your own to see if you're getting it. All right, so if I do the value at 2, let's look. Right here is where it changes concavity. Okay, and then it's going to be coming back up. All right. And I know that's kind of hard to visualize on a graph. All right, so I want you to find all these things for this next function. All right, again, pause the video and see if you can find everything. I'm going to start with the extreme values. Okay, remember, that's when the first derivative, okay, which is this right here, is equal to 0. This is one that's easy to be factored. And plan on doing some of this without a calculator. If I take out a negative 6x, let's see, that's going to make x minus 2. Well, when is this set equal to 0? X equals 0 and x equals 2. All right, now I need to find the second derivative to do the second derivative test. All right, the second derivative is negative 12x plus 12. All right, when I plug these values in, okay, when I plug in x equals 0, all right, I get, I'm going to call it f. All right, is, let's see, when I plug in 0, it's positive, it's greater. So what does that tell me? When it's positive, it's a relative min at x equals 0. Okay, and then let's look at x equals 2. All right, so f double prime of 2. Okay, that makes negative 24 plus 12, so that's less than 0. It's negative, so I have a relative max at x equals 2. All right, moving right along. Increasing and decreasing. Remember, you're looking at the first derivative. And we can draw sign lines, but we have to be, we have to give a little bit more explanation. All right, I'm putting my critical points when I set it equal to 0 on here. And I got to find where is the first derivative, negative and positive. All right, so when the first derivative on this side, say negative 1, all right, let's look at it. And I like to look at the factor form because when I plug negative 1 in here, that goes positive, that's negative. So it's negative, it's less than 0. Okay, f prime of, let's say, positive 1. Okay, that's negative and that's negative, so it's going to be positive. All right, and f prime of 3, that's negative, that's positive, so it's going to be negative. So it's increasing on the interval from 0 to 2, and it's decreasing when it's negative, so from negative infinity to 0 and 2 to infinity. All right, let's look at concavity. Concave up, concave down. Remember, we're looking at the second derivative. All right, and it's when the second derivative, all right, is set equal to 0. Well, the second derivative is negative 12x plus 12. And when I solve this, I get x equals 1. Double check your math. Make sure you're getting that. All right. Okay, so we need to check concavity here. Well, here, f double prime, something on the left, say 0. When I plug 0 into the second derivative, I get a positive. So it's greater than 0. And then here, when I plug in something on that side, say 2, all right, that's going to give us a negative value. All right, so therefore, it's going to be concave up from negative infinity to 1 and concave down from 1 to infinity. Now there's one last thing we can decide. We can decide if we have points of inflection. Now it's when this equals 0, we got x equals 1. All right, but the other case is, does it change concavity? And here it does. It went from positive to negative. So I have a point of inflection at x equals 1. So be able to practice this, be able to do it, and be able to do it without a calculator. You can verify it on the calculator to see, okay, is it increasing or decreasing on these intervals? Is this where my relative min and relative max are? Concavity, you can kind of see that on a graph. Sometimes it is a little difficult. It's also a little difficult sometimes to see that point of inflection, but you can kind of see that change in concavity.